Hello, and welcome to our webinar, Characterizing Ceramic Materials, a deep dive into particle size and dispersion stability, presented by LabCompare and sponsored by Bettersize. My name is Michelle Taylor, and I am the editor-in-chief of LabCompare. Before we begin, I would like to review a few housekeeping items with you. Please take a moment to familiarize yourself with the user interface for today's webinar. The large window with the heading Presentation is the primary window for today's webinar. You should be seeing the welcome slide there right now. Just to the right of the main presentation window is the speaker bio window with a little background on today's presenters. On the left side of the screen, you will see a Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed into the queue for the speaker to address when we get to the Q&A portion. At the bottom of your screen, you'll see additional buttons to enhance your webinar experience. To see what a particular button does, just hover your mouse over it and a tooltip will appear with the button's function. Now, allow me to introduce today's speakers so we can get started. First, you will hear from Dr. Frederik Schleife, who is the European Sales and Product Manager of Bettersize product line at 3P Instruments. He earned his PhD in organic chemistry from the University of Leipzig, Germany. After gaining early experience in technical sales of particle and distribution characterization instruments, Freddie assumed responsibility for managing the European sales network in 2018. Since then, he has been dedicated to expanding the presence of Bettersize instruments across Europe and supporting their successful market integration. Wenjian Zhou is an application scientist at Bettersize Instruments. He received his bachelor's degree in applied chemistry from Shenzhen University and earned a master's degree in chemistry from the University of Marburg. Since joining Bettersize, Wenjian has specialized in application research using laser diffraction techniques and has been dedicated to providing solutions for both offline and online particle size measurements. Now, without further ado, I will hand it over to Frederik to get us started.
Thank you for this kind introduction, and hello to everyone also from my side for today's webinar about the characterization of ceramic materials. So my first part will mainly focus on the manufacturing process for ceramic itself. And therefore I will start with guiding you through some fundamentals to bring you right on board. Before we head over, that I will present you some the influence, more in detail, the influence on particle size and true density, as well as slurry stability on the manufacturing process, as well also for the final workpiece in the end. So let's start with some fundamentals and talking about ceramics. The question is, what is a ceramic? And ceramic materials are very diverse in terms of their properties and therefore also in the resulting applications. So to give you some relevant examples, one of maybe the most popular ones is alumina. So alumina is mainly used for structural ceramics, like it can be used for cutting tools or also in ultrasonic technology. But furthermore, due to its great biocompatibility, it can also be used for bioceramics as a dental material and prosthetics. Another example would be lead zirconate titanate, which is mainly used for functional ceramics, like in sensor technology and ultrasonic technology. And last but not least, the third example I want to present today is silicon carbide, which is mainly used for oven technologies or also slide rings. But furthermore, it can be used as a so-called composite ceramics, for instance, in gas turbines or in aerospace technology for high performance ceramic. What all of those materials have in common is that their structure is a crystalline structure. Even if the nature of the crystalline structure could be different, like rhombohedral, perovskite, or hexagonal type, but all of those are of crystalline structure. And this results in relatively high melting temperatures, like you see here, more than 2000 degrees Celsius, or at least above 1000 degrees Celsius. So what all of the ceramics have in common is that they are very brittle, that they are hard, and come with high melting temperatures or high melting materials. So in these properties, they force the processing of ceramics, manufacturing of ceramic workpieces, to have a rather challenging process. what is used so-called powder shaping and sintering afterwards. So compared to metals, they cannot easily be melted and poured somewhere to get them in a new shape. So they need this rather complex process of powder shaping and sintering. So, and here's how this process is done. So it all starts with raw materials. These are the starting powders, but not only the powders, like alumina, zirconia, or others. It is also the dispersion medium that is needed and some additives. Additives to get the final properties right in shape for proceeding with the process. So what is next is it could be milling to adjust the particle size of the raw material, but not only milling to get it smaller, it could also be granulation. Why granulation could be needed, especially if the powder needs to be transported somewhere, it could be advantage if you bring them together to granular material, which eases the transportation, for instance, of the powder material. Furthermore, they could be mixed, either two different dry powders mixed together, or mixed in a kind with the liquid medium to form a dispersion. After this further material processing, it gets over to the very important step of the shaping process. So with this shaping process, the so-called green body is produced, is manufactured. And this can be done in different ways. We will see in one of the next slides. It can either be done in a wet process, like it's done with slip casting or spraying. And it can also be done in a dry process when it's printing presses or hot presses. So, but this step here brings the final shape of the piece you want to manufacture and forms the green body. But still more like individual particles that are pressed somehow together, they need to be sintered together to achieve the final performance of a workpiece. So this sintering process at really high temperatures leads to a compaction and a consolidation of the individual particles to give the material its final properties. And last but not least, depending on the application, there's a final finishing. It could either be grinding or polishing or final shaping, depending on whether it's more for dental application or other high performance applications. You bring the final shape and polishing on the material. The sintering process or the shaping process could be like shown here, 2 individual steps, but sometimes for such special processes, it could even be only in one step, in one process step. For instance, with the hot isostatic pressing, here you get a shaping and a sintering in just one step. So, and as you might have realized, I already gave different names for different processes, but basically they can be divided into 2 groups for this shaping process. It could either be the dry shaping process, like dry pressing, cold isostatic pressing, but also hot isostatic pressing. I said for this, it already combines the shaping and the sintering process. But you can also shape these materials in a wet route, in a wet way. And some of those processes are mentioned, like injection molding, slip casting, gel casting. So simply making a dispersion from powder and a dispersing medium and pour it somewhere to get the green body formed during those processes. Which process you might select might mainly depend on what is the typical application later on. So if you go for dry pressing, you might only achieve such simple geometries or plates. Maybe this is really cost effective, but does not allow you to bring high performance or to form high performance ceramic material. For others, if you need hard densities or really high performance, you might rather go for some of the wet processes, like slip casting, tape casting, or even tape casting 3D printing, where you can achieve really complex structures or finer work pieces with hard density and high performance. So as maybe the wet process is quite often used. For the next slides and the next part of my talk, I'd like to focus on the wet forming process. So obviously, as it's already mentioned several times, there seems to be an influence of particle size distribution, but also the true density of the starting powders on the process and therefore on the product properties of the ceramic later on. So let me give you just two brief examples which different type of size and which size range we are talking about. So ceramic starting materials are available in various sizes and various distribution widths, depending in the end on the application. One example here is a sub-microscale zinc oxide, which is used for the production of resistors. You see a particle size distribution where the majority of the particles are below 1 micrometer. So, and this is what is typically used for such an application. Furthermore, there are other applications, like here's an example of a microscale iridium tin oxide granulates, which are used for electric conductive layers. So you see here, maturity is a relatively small, distributed, narrowly distributed, normally distributed here shortly below 100 micrometer. So there's not really typically to say all ceramic raw materials needs to be below 1 micrometer or needs to be around 100 micrometer. It really depends on the application itself. So the particle size and its distribution of a starting powder significantly influences the properties of the end product, in particular regarding the shaping process, but also this later on the sintering process. And this is what I want to explain to you why and how it affects these processes. So first of all, let's talk about the influence of the particle size distribution on the shaping process itself. So during the formation of the green body. So what is the main aim of the shaping process? The main aim of the shaping process is that the green body structure later on comes with a high density, comes with a homogeneous pore structure, and comes with small pore sizes. Why are these three properties of the green body are important? A high density is needed to minimize later on a shrinkage during the sintering process. So when the green body, after the green body is formed and the green body is sintered, this sintering effect will lead to a shrinkage. So if the density of the green body is not small enough, it's not high enough, if we don't have a high enough density, then you get a higher shrinkage. So, and this is of course not desired, as you want to have during the sintering process to keep with the dimensions you gave the piece at the end during the green body formation. So why is a homogeneous pore structure needed? Because you need to know that different pore sizes will behave in a different way during the sintering process. So the larger the pores are, the higher will be the sintering temperature that needs to be applied during the sintering process. The smaller the pores are, the lower could be the sintering temperature. So when you have an inhomogeneous pore structure, you might have some large pores next to some small pores. When it comes to sintering, you would see that those larger pores might even grow in the sintering process, which give later on a lower density of the final wet piece after the sintering process. So a typical phenomena is that when you have an inhomogeneous pore structure, the smaller pores, the amount of smaller pores will decrease, and of larger they will even grow on the expenses of the small pores. So to achieve a high sinter density in the end, a homogeneous pore structure is needed, no matter if large or small, but it needs to be homogeneous. Anyway, still, smaller pores are desirable and are beneficial against larger pores, because the smaller the pores are, the smaller is the sintering temperature. So therefore, you need to sinter at higher temperatures for larger pore sizes. Furthermore, a smaller pore structure give you a higher green body strength, what is also beneficial, especially if you want to transport the green body somewhere, to make sure that it would not fall apart. So therefore, smaller pores are favorable against larger pores. For this, I want to give you an example. I want to show you an example, and this is the manufacturing of a zirconia green body via a wet shaping process during a so-called electrophoretic deposition. So therefore, there was a dispersion of a mixture of coarse and fine zirconia powders in water with a pH value around 10. And there was a variation of the mixing ratio of fine and large zirconia powder. And it could be investigated by the pore distribution and also the density later on, how different mixtures or different ratios and mixtures of coarse and fine zirconia would behave later on or would affect the final process. So here you see some electron microscopic images of this coarse zirconia with a D50 of around 3 micrometer. While the fine zirconia comes approximately with a D50 of 150 nanometers, or 0.15 micrometer. So on this slide, on the left-hand side, you can see the size distributions of the pure coarse zirconia and also the pure fine zirconia next to each other. And again, the microscopic images. So how does it influence the shaping process? With different mixtures of the coarse and fine zirconia, we made some green bodies and investigated their porosity with the help of a mercury intrusion. Mercury intrusion. So here you can see the measurement of the pore radius in nanometer and the relative pore volume of different mixtures. So the red curve represents the pure fine, the pure coarse zirconia, so with 0 weight percentage of fine zirconia. So for the pure coarse zirconia powder, further processed to a green body, you would see a pore radius of around 400 nanometer. When you mix the coarse powder with a bit of the fine powder, so with 10% of fine powder, and you measure again the green body density, you will see pore radius distribution from the blue curve. So different than for the pure coarse zirconia, which gives a normal monomodal distribution of the pore sizes, the 10 weight percentage of fine zirconia and 90% of coarse zirconia powder results in a green body with a bimodal pore size distribution. So you might get here some pores in a range of around 160 nanometer and some pores in a range of 35 nanometer. But finally, when you mix 16 weight percentage of the fine zirconia into 84% of the coarse zirconia, you achieve a green body density with only a monomodal pore distribution of around 35 to 40 nanometer. So therefore, you can see that depending on the mixing ratio and therefore depending on the final particle size distribution of the mixture, you can achieve different pore radius and therefore affect dramatically the performance of the shaping process. So remember what I said before, the smaller the pores, the lower the sintering temperature, and next to it, it is desirable to achieve monomodal pore distribution to later on get higher on sintering densities. It seems that the 16 weight percentage in 84% of fine zirconia and 84% of coarse zirconia seems to be the advantaged and desirable mixture here. So this could be further proved by checking the sintering process. So after those green bodies had been sintered, you can realize that when there's no fine zirconia added, you only have the 3 micron coarse zirconia powder, and you sinter the green body at 1600 degrees Celsius for 3 hours, you would realize that you do not get a closed structure. So you have still a large pores in, so the final density is pretty low, and you cannot await a good performance of this piece of ceramics. Okay, maybe it was simply too low the temperature, so therefore it was sintered at 1700 degrees Celsius for 3 hours. Then you can see that sintering performance is already better, but still there's a lot of open cell content here. There's a lot of enclosed structure, so therefore still not what you want to get for a good workpiece. But when we take the 16 weight percentage fine zirconia and 84 weight percentage of coarse zirconia, and we perform the sintering process at 1600 degrees Celsius for 3 hours, we can achieve an almost really dense structure with only a few pores left, as you can see here on this image. But then increasing the temperature to 1700 degrees Celsius for 3 hours, you could see that you can really achieve a closed structure, and you can await a good performance of the final ceramic workpiece here. So therefore, I could show you that adjusting the particle size distribution of the raw material you will use for the process has dramatic effect and dramatic influence either on the green body stability or green body properties, and furthermore also, of course, during the sintering process on the final ceramic piece. So to summarize this a bit, I could show you that when you use the pure coarse zirconia with a log normal distribution of around 3.4 micrometer, you might get in the green body one rather narrow peak for the pores for around 400 nanometer, but with the lowest relatively green density, lowest sinter density, either on 1600 or 1700 degrees Celsius sintering temperature. Yeah, by increasing a ratio of a fine zirconia up to around 10 weight percentage, we got a bimodal size distribution with a D50 of around 3 micrometer. But for the pore size distribution in the green body, we got a bimodal distribution. So we got small pores and larger pores, resulting in a medium, relatively green body density, sintering densities. And finally, when you use 16 weight percentage of the fine zirconia, we got a bimodal size distribution with a D50 of around 2.8 micrometer. We get one pore peak for the 38 nanometer pore radius, but we achieve really high densities either for green body and also for sinter bodies. So this for the influence on particle size, but what else can we do with the powder to analyze the ceramic raw material? So another factor that affects later on the process is the true density. So I want to show you how the true density can affect the starting powders, or the other way around, how the different densities of starting powders can affect later on either the process or the performance of the final ceramic pieces. And therefore needs to mention that the true density of starting powder provides an important information about the crystal structure, but also impurities. So depending on what is your raw material, for instance, alumina or zirconia, of course, they have different true densities. And you can imagine, in case there are some impurities in your starting material, you might measure a density different of the density of a pure alumina or pure zirconia. So therefore, true density measurement can already be a quality indicator for the regarding the impurities of the raw material. But furthermore, also those materials come with different crystal structures, and these also could be measured or could be identified by measuring the true density. So, and furthermore, on the final sintered ceramic, you can also measure the true density, which give you again information about the crystal structure, but also about the sinter density. So let me show this to you on one example, how you can identify, with the help of the measurement of the density, you can identify which crystal structure you have, and maybe if it's the right one you want to have. So on the example of a zirconia ceramic, I want to let you know that zirconia, there are different crystal structures known. So one is a monoclinic structure, which has a true density of 5.7 gram per cubic centimeter. So and this monoclinic structure is stable at room temperature. But furthermore, there's another structure, which is called a tetragonal structure, and this comes with a higher density of 6.1 gram per cubic centimeter. So you see, when it comes to a transition from monoclinic structure to tetragonal structure, there's a loss in volume of around 3 to 5 volume percentage, resulting in a higher true density. So this tetragonal structure is the desired one, but there's one issue, and this is that tetragonal structure is only stable around above 1170 degrees Celsius. Why? I said this is the desired one. I will show you later on. There are also applications where you want to have a monoclinic structure, but for some applications, tetragonal structure is the one we want to have. So to get them stabilized also at room temperature, it is typically used a mole percentage of yttrium oxide. And with this yttrium oxide stabilized zirconia modification, we can achieve to have this modification to be stable at room temperature. Yeah, so therefore, with doing or stabilizing the zirconia crystals with yttrium oxide, you might achieve or you will achieve a way more stable tetragonal structure at room temperature, which results here in a true density of 6.03 to 6.08 gram per cubic centimeter. So what is a typical application for this tetragonal structure and why this might be the one you want to have? Those stabilized ceramic powders, they can be used to produce ceramics with extremely high strength. Why? Because there's an effect that's called crack shielding by transformation toughening. And what's that? So if you would apply an external force on such a tetragonal zirconia ceramic workpiece, you apply a force, and this leads to a crack. The following effect prevents the crack traveling through the entire system. When there's a crack, this crack leads to a spontaneous stress-induced tetragonal monoclinic phase transformation, also called TM transformation. And at the crack tip. So due to the stress that is applied here, the tetragonal structure will undergo a transformation into the monoclinic structure. So as you remember, the monoclinic structure comes with 3 to 5 percentage larger volume. So and this increase in volume spontaneously will prevent that the crack can further travel to the entire ceramic workpiece. So when it would be only a monoclinic structure here, when there's a crack at one point, this crack might go through the entire piece and you cannot use it anymore. But for high performance ceramics, like in dental, for tooth, for instance, you use those tetragonal structures, because then this prevents that there's a crack and that in the end it will be destroyed once there's a single crack somewhere. So therefore, when you want to manufacture such a workpiece here, it requires a starting powder with a tetragonal phase, and the tetragonal phase content should be as close as possible to 100%, so no monoclinic crystal structure in there. So therefore, if you measure the true density of your starting powder in a range of 6.03 to 6.08, you know that this zirconia powder is almost completely in the tetragonal phase, so and therefore it is suitable to manufacture a ceramic like this. So last but not least, let's discuss about how the slurry stability might affect the manufacturing process or the manufacturing of the final workpiece. So slurry stability is of interest and is important when it's about the wet route for the shaping process in ceramic manufacturing. So you can imagine, or as we already showed the slide before, the density of ceramic raw materials is relatively high, and especially compared to water, it is maybe 5 to 6 times the density of water. So you can imagine that those ceramic particles might pretty fast start to settle down, to sedimentate in a liquid phase. So therefore, if the particle size is even too high, you get a really fast sedimentation. So therefore, to have a smaller particle size would prevent for a longer time the sedimentation of the particles. Yeah, if the material density of the particles is very high compared to the media of water, or also the viscosity of the medium is pretty low, you might also get really a fast sedimentation. The material density you might not be able to effect, because when you want to have a final workpiece made out of zirconia, obviously you need to use zirconia particles. Maybe the viscosity of the medium could be adjusted with some thickeners, some additives. But yeah, so this is the first thing. Sedimentation could be an issue. And a second destabilization effect that is an issue in the manufacturing of ceramic pieces is any accumulation. So if you have too small repulsive forces, electrostatic or steric, between the particles, or you have a really high solid content in your ceramic slurry, those particles might tend to accumulate, and therefore you don't have a stable particle size. And as shown before, when there's the particle size change over the process, then of course you cannot make sure or secure that you will have the final properties you desire. So usually both effects are overlap with each other, and I'll show you an example which makes it pretty clear that here sedimentation or accumulation would be an issue. So, and this is a negative effect on the manufacturing process on the example of tape casting of a ceramic slurry. So this tape casting process works in a way that you have a ceramic slurry which is applied here with some plates onto a so-called tape carrier. So therefore you have a tape running here, and the slurry is forming a kind of a tape. So it undergoes here through a drying chamber. So therefore you could basically form a dried ceramic tape that could be rolled here in this shaping process. So, but you can imagine if the slurry would sedimentate, you get a separation based on a solvent content and a particle size. So that means at the beginning of the process, you will get a lot of large particles, and later on, finer particles, which leads to an inhomogeneous dried tape here during the shaping process. And also when it comes to slurry accumulation, there's a change in the slurry processing. So maybe the viscosity might change during the process, which also leads to inhomogeneous processing here. So furthermore, during the drying process, an homogeneous pore structure in the green body will lead to a cracking, and in the end, to a less smaller green density. So therefore, in the sintering process, if this is heterogeneously formed here, you might find a change in the sintering behavior from different tape sections and some sinter crack formation due to the pore structure that is not like you desired it. So therefore, particle sedimentation and accumulation are likely destabilization effects in ceramic slurries, and you need to try to prevent them, or at least to analyze them. So both effects have a negative impact on the shaping effect and the properties of the resulting green body, which leads to inhomogeneous pore structure, a change in the green density, and last but not least, the sintering properties might be negatively affected by this, with a probability to a crack formation during the sintering increases. So let's come to an end for the first part. I'd like to show you, or with this I want to hand over to the second part. So with a laser diffraction, I hope I could show you that the particle size has a major effect on the process itself. So therefore, the laser diffraction is a supporting measurement method for investigation and optimization of the ceramic manufacturing process. And one instrument that allows you easily to characterize such powder materials, but also later on the slurries, is the Bettersize 2600, which comes either with a wet dispersion module BT802 and a dry dispersion module BT902, which allow you either the characterization of dry or wet samples. So why is this widely used, and what are the advantages of the laser diffraction? First is that laser diffraction gives you a really broad and large measuring range. The measuring range for the Bettersize 2600 starts already at 20 nanometer and goes up to several millimeters. So therefore you can span really a wide range, and no matter if it is more the submicron ceramics or it's the micrometer particles, they can be measured. Dry and wet dispersion is available. A laser diffraction measurement is pretty fast. You get a result within a few seconds, and it gives you very good resolution. So even if you mix different powders with each other, you could easily resolve a multimodal distribution. So therefore, you can easily monitor the quality of the starting powders, your raw material, and you can also monitor any granulation or milling processes, or later on identify and indicate heavy agglomerations if you check for the final slurry. And even better, if you combine on a modern approach the laser diffraction with dynamic image analysis, like it can be done with the Bettersize 2600 and the PIC1 imaging module, you get additional particle shape parameters for further specification of your powders and particles. And in a combination of laser diffraction and dynamic image analysis, you can even increase the accuracy in the coarse range, which might show you if there are any oversized particles in there. So again, it works pretty well for the raw material with additional information and improvements for feeding compaction or others. And also you can analyze get an additional information for your slurries, like the flow behavior, the slurry solid content, and others. And to analyze the dispersion stability, there's one instrument or one technique that is widely used as static multiple light scattering for the qualitative and quantitative characterization of ceramic slurries, which with the B-scan lab, and you will see this in the second part, with the B-scan lab, you can analyze sedimentation and or agglomeration behavior of those slurries in a great way. So it gives you really a qualitative verification of the effects of sedimentation and agglomeration. It allows you to quantify those destabilization effects via the so-called instability index, and it offers you even concentrated and or diluted dispersions by measuring in transmission and backscattering. So this is mainly the stability test for the finer ceramic slurry. So that's for my first part, and with this, it's my pleasure to hand over to Wenjian for the second part, where we get more details about the analysis itself, the technique itself, and the instruments that are used to characterize the ceramic materials.
Thank you, Freddy, for your comprehensive introduction. Hello, everyone. I'm Wenjian, an application scientist from Bettersize. We have just learned how ceramics are made, from raw mineral to finished products, and why particle size plays such an important role across the manufacturing process. We also saw how true density and slurry stability affects the quality of ceramic. In this slide, I will explain how these parameters can be measured and share some real application cases. In the part 1, I will demonstrate the measurement principle of laser diffraction and dynamic imaging for particle size and shape analysis, and the benefits of combining these two techniques. So, what will happen if we don't carry out particle sizing? The answer is that the product's quality cannot be guaranteed, because uncontrolled particle size often leads to structural defects. There are various processing methods for ceramic material, and the particle sizing can be performed in several critical steps. For example, particle sizing can be used for quality control to monitor the particle size of raw material, or to evaluate whether the material is evenly mixed before further processing. Shaping is a crucial step in ceramic manufacturing. And different shaping methods specify different requirements on particle size and distribution in powder. Here I will list some examples. In dry pressing, ceramic powder will be filled into a die and pressed by punches, whose particle size and distribution needs to be specified to make sure good packing efficiency. Sometimes particle sizing for granule is also necessary, since granule with appropriate size increase particles flowability. In slip and tap casting, ceramic slurry will be poured into a mold. Control of particle size is critical since the slurry stability is greatly affected by particle size, and a stable slurry reduces the possibility of cracking or warping. In injection molding, powder and a binder are injected into mold. Particle size defines the flowability of the feedstock, the binding efficiency, sintering performance, and the mechanical strength of the final product. In general, smaller particles are usually preferred because they promote densification and thereby improve the product's performance. In 3D printing, particle size and distribution needs to be optimized to balance the flowability, densification, sintering performance, and packing efficiency. On the previous slide, we learned how particle size affects the manufacturing of ceramic product. But then comes to the question, what is the most popular way to measure particle size? So the answer is the laser diffraction technique. In this slide, we will figure out how we use laser diffraction to analyze particle size. Imagine a particle in the measurement zoom, and it is irradiated by a laser beam, so a part of light gets scattered. Scattering can be considered the combination of 4 light phenomena, namely reflection, attenuation, refraction, and diffraction. Let's focus on the right part of the slide. If the particle is large, most of the light is scattered in the forward direction, resulting in a diffraction pattern with an intensive central spot. As the particle size increases, the central intense peaks becomes narrower in the diffraction pattern. Suppose there are many particles in the sample cell. The overall pattern can be considered the superposition of diffraction pattern caused by individual particles. These scattered signals are then received by the detectors and further processed by the software to calculate the particle size distribution based on Mie theory. We have gone through the basic principle of how laser diffraction works to determine the particle size. Let's take a closer look at the actual particle size analyzer. An illustration of simplified interior structure is shown on the right side. In general, samples need to be added to a dispersion module and transported to a sample cell, where they will be irradiated by a laser beam, producing scattered signals to be analyzed by the software. What Bettersize can offer is Bettersize 2600 Laser Diffraction Particle Size Analyzer, which provides reliable and accurate measurement with its patented optical design ranging from 0.02 to 2600 micrometers. This instrument is also characterized by multiple dispersion modules, allowing to handle a wide range of samples, from dry powders and liquid suspensions to organic materials, and even valuable samples with small volumes. What's more is the Bettersize 2600 can be equipped with a dynamic imaging system, which enables the measurement of coarse particle up to 3,500 micrometers and provide detailed particle shape parameters. And an auto-sampler is available for fully automated measurement of up to 60 samples with just one click. In this way, the Bettersize 2600 not only offers a versatile dispersion modules for different sample types, but also enables dynamic image analysis for detailed particle size shape characterization, and supports fully automated measurements by using a dedicated auto-sampler to minimize human intervention. As we know, the laser diffraction system already provides a wide measurement range. So why we combine the laser diffraction systems and the dynamic imaging system and what benefits can we get from this combination technique? Let me answer the first question. Why we need dynamic imaging system? Suppose there are few coarse particles exist among a large number of small particles. The scattered signal intensity from the coarse particles is very weak compared to that from the small particles. As a consequence, the scattered signals caused by the coarse particles are hidden, appearing either as noise signal or as part of the scattering contributed by the small particles. Image analysis solves this problem by capturing images of individual particles, including the few large ones, and processing them to generate size and shape parameters. Images do not lie. They provide intuitive results so that we won't miss coarse particles, and up to 24 particle shape parameters can be provided, including circularity, ferrite diameter, and aspect ratio. Besides, dynamic imaging system is highly sensitive to coarse particles, extending the upper measurement limit to 3,500 micrometers. The outlier particles, such as bubbles and agglomerates, can be reviewed because each particle is photographed, which can further be used to evaluate whether the dispersion status of the sample is good or not. Two cameras with different magnification are installed in the dynamic imaging system to ensure clear images of every particles. Therefore, measurement accuracy can be guaranteed. Here is a real case that shows why it is important to detect unexpected particles. The sample here is zirconia powders, which we disperse in water for full dispersion. As mentioned earlier, even a small amount of abnormal coarse particles can significantly affect the final performance of the product. Let's focus on the particle size distribution curve. If we only use laser diffraction, we get an orange curve, and everything looks normal, and there is no signal of abnormal coarse particles. But when we activate the combination test, something interesting happens. We can see there is a small ghost peak at around 120 micrometers. And when we check the individual images of the particle, we can notice that there are particles whose size are around 120 micrometers in the sample. This indicates the high sensitivity of dynamic imaging system to coarse particle. Okay, we already know how to measure particle size by combining laser diffraction technique and image analysis. Let's shift to another important parameter, the true density. The true density is defined as the mass of the solid material divided by the volume it actually occupies, excluding the volumes of open pores, closed pores, and the interparticle pores. True density is essential in ceramic manufacturing, especially in the shaping step, as it provides a basis for evaluating sintering behavior. It can be used to help us understanding porosity. By comparing the true density and the bulk density of a sample, we can calculate how porous the product is. This is critical because applications have different requirements on porosity level. For example, structural ceramics are made of dense material for strain, while catalysts need high porosity for specific surface area. And the true density allows us to optimize slurry solid loading. When preparing a slurry for casting or 3D printing, knowing the true density ensures the right particle volume fraction, which can prevent structural defects. True density also helps us predict the shrinkage and the final dimension. Using true density, we can calculate how much shrinkage to expect and optimize design so the final part is the correct size. In short, understand it let us achieve precise and high performance ceramic every time. So, How can we test true density quickly and convincingly? The answer is using a gas speculometer. Before getting to know what a gas speculometer is, we need to understand the principle behind. The key of the principle is Boyle's law, and it demonstrates that a gas pressure times the volume is constant when the temperature and the mass of the gas are constant. By applying this law, let's see how a gas speculometer calculates the true density. A typical gas speculometer has a sample chamber, a reference chamber, a pressure transducer, and three main valves: the fill valve, expansion valve, and a vent valve. Imagine we are using a gas speculometer now. We start the measurement by opening the lip and placing the sample in the sample chamber. Close the lip, keeping the expansion valve closed. Open the fill valve to allow a specific amount of gas to enter the sample chamber. Then close the fill valve. The pressure at this point is recorded as P1. Next, we open the expansion valve, allowing the gas to flow through the sample chamber to the reference chamber. Once equilibrium is reached, the pressure is measured as P2. Suppose the volume of the sample is V, and we can use Boyle's law to obtain two equations. The volumes of the sample chamber and the reference chamber are already known, along with the recorded values of P1 and P2, so the volume of the sample can be calculated by the software. With the sample's mass easily obtained with a precise balance, we can then determine the true density. With the gas speculometer from Bettersize, we benefit from enhanced capabilities. The Betterpic 380, combined with its user-friendly software, provides extensive measurement options, including volume, density, solid content, and open cell content, making it suitable for a broad range of applications. It offers rapid, highly accurate measurements with an accuracy of 0.02% and operates within a flexible temperature range of 10 to 65 degrees Celsius, accommodating diverse sample conditions. The system can also be equipped with 316 stainless steel sample cups, ideal for handling corrosive material like cement to ensure long-term durability. With a volume capacity ranging from 1 to 100 cube centimeters and automatic chamber volume matching, it adapts to various sample sizes. In summary, the Betterpic effectively measures hard forms, liquids, solids, semi-solid mixture, and slurries, making it a highly adaptable solution across the industries. Based on the measured volume and the true density, three interior stabilized zirconia ceramics were analyzed to evaluate the porosity level of the material to determine the appropriate 3D printing parameters for ceramic prostheses. If the porosity level is high, the green body shrinks greatly after sintering, probably leading to structural issues or non-specific size. Understanding this parameter is crucial because they directly affect the final dimensions, mechanical properties, and overall performance of the print ceramic parts. Samples with a porosity level between 10 and 15% are generally considered good. We measured 3 samples, and sample 1 performed better than samples 2 and 3 because it has the lowest porosity level. So far, we have talked about 2 techniques for measuring particle size and the true density in dry powders. Now, let's shift our focus to something different. A method that helps us understanding the stability of a liquid suspension. So, what do we mean by stability? In general, stability is the ability to resist changes. When we talk about dispersions, it means how well the particles can stay evenly distributed without sedimentation and flocculation. Now, What actually affects this stability? First, we look at interparticle force. On one hand, we have van der Waals attraction, pulling particles together. On the other hand, we have electrostatic repulsive force, pushing them apart. The balance of these two is explained by what we call the DLVO theory, which describes how this force changes as the particles get closer or farther from each other. Moving on to the right side, let's think about steric hindrance. This happens when polymers or surfactants coat the surface of the particles, creating a physical barrier. That barrier makes it harder for particles to stick together, which helps improve stability. Next is particle size. Smaller particles move more actively because of Brownian motion. This random motion helps keep them from sedimentation and reduce the possibility of aggregation. Another important factor is the particle density. If the suspended particles are much heavier or lighter than the liquid around them, they tend to settle or flow more easily, which lowers stability. And finally, we shouldn't forget about other conditions like viscosity, temperature, and the pH. All of these can influence how stable the dispersion is. We have talked about the factors influence the dispersion stability. The next question is, how can we actually evaluate the stability? The answer is static multiple line scattering technique. It is an optimal method to evaluate stability by detecting the variations of transmit and backscatter signals. If the signal variation is slight, that means the changes in the dispersion is slight as well, and in turn, the slurry is stable. Here I demonstrate how SMLS works. A setup that contains an LED, a forward detector, and a backward detector moves vertically along the sample cell to capture the transmit and the backscatter signal every 20 micrometers. For transparent samples, we use forward detector to capture the transmit signal. If the sample is opaque, we use backward detectors, since in this case, transmission is almost blocked. Let's take sedimentation as example. Suppose the sample cell is placed horizontally, so the x-axis represents the height of the sample cell, and the y-axis is the reference backscatter signal. Over time, we observe that the signal increases at the bottom and it decreases at the top. What does this mean? It means the particle concentration is increasing at the bottom and falling at the top. In other words, the particles are settling. So, by analyzing how and where signal changes, we can qualitatively understand the unstable phenomena. In addition to qualitative analysis, we can also perform quantitative analysis using what we call the instability index, or IUS. IUS is calculated by accumulating the variations in light intensity between two consecutive scans. The principle is simple. If the light intensity changes a lot, the IUS value goes up. And the higher the IUS, the less stable the system is. Now, because each scan provides a new IUS value, we can generate an IUS trend curve over time. This allows us to see not only how quickly the IUS increases, but also how long it takes for the IUS to reach a certain value. What's more, we can also use this IUS to compare different samples. By looking at their IUS values, we can directly figure out which slurry is more stable. At Bettersize, we offer the B-Scan Lab, which utilizes the SMLS technique to analyze slurry stability. The measurement process is non-invasive, simple, and fast, meaning we can measure the sample directly, without any preparation. And thanks to its optical system, the B-Scan Lab can handle a wide range of samples, from diluted and transported ones to opaque samples with high solid loading. The signals are captured every 20 micrometers, and because of the scanning interval is so small, even the most suitable variations in light intensity can be detected. For efficiency, up to 10 BitScanLab units can be connected to a single computer, allowing 10 individual measurements to run simultaneously. This not only increases the operational flexibility, but also saves valuable time. Temperature control is available from room temperature to up to 80 degrees Celsius. This makes it possible to stay stability under high temperatures, or to track how the IUS changes with different temperatures. Finally, we offer 3 types of sample cell. In addition to the standard cell, we have a coring cell, which is designed for highly viscous samples, and a low-volume cell used for valuable samples. Let's take a look at a real case of stability evaluation. In this measurement, we measure 4 zirconia slurries. At first glance, all 4 samples look exactly the same. In fact, no changes could be observed with our naked eyes. In this case, we need to ask BitScanLab for help. In most cases, slurries are highly viscous since their solid loading is very high. The samples are concentrated and opaque, so we rely on backscatter signals rather than transmit signals. Because the slurry is so viscous, the particles move very slowly. As a result, the changes in light intensity are quite small. But even if the changes are suitable, we can still compare their IUS values. The IUS value for 4 samples were relatively small, which indicates good stability overall. However, when we compare their IUS trend curves, we notice that the sample A shows a sharp increase in IUS at the very beginning, and then the increase slows down, and the sample A is the most unstable during the measurement. But the IUS values of the samples B and C grow rapidly later on, and probably exceed sample A if we extend the measurement time. Here are the key takeaways from today's talk. First, particle sizing really matters. It has a direct impact on ceramic products quality. With the Bettersize 2600, we can combine laser diffraction with dynamic imaging. That means we can not only detect coarse particles that might be missed by laser diffraction alone, but we can also analyze particle shape. Next, true density measurement is equally important. Using the BetterPic, we can easily measure the true density, which helps support the correlation between the powder and the final part density, and thereby evaluate the product's performance. And finally, when it comes to the slurry stability, the static multiple light scattering technique gives us both quantitative and quantitative insights. The BitScanLab makes this process flexible and efficient, with high scanning resolution, precise temperature control, and multiple sample cell options. That's all I'd like to share today. Thanks so much for listening. And Dr. Freddy and I would be happy to answer any questions you may have.
All right. Thank you, Freddie and Wenjian, for your informative and interesting presentations. We now have a few minutes for the Q&A. So if you have a question for our presenters, please take a moment now to submit it. And a quick PSA while you do that. This year actually marks Bettersize's 30th anniversary, and they're marking this milestone with something special: a free 3-year warranty on all new purchases. With 106 patents powering innovation and 22,000 plus organizations worldwide trusting Bettersize, there's no better time to upgrade or expand your lab capabilities. If you've been considering a new purchase, now might be the perfect moment. All right, I see a bunch of questions coming in, so let's get started. Freddie, a first couple ones that have come in are for you. Are you ready for us?
I am. Please go ahead, Zhou.
All right, so you demonstrated how different proportions of fine zirconium dioxide powder affect green and sinter density, with the best results achieved with only 16% fine zirconia powder. Would a larger amount of fine powder therefore achieve even higher green density or enable sintering at lower temperatures?
Yeah, so that's a good question. Of course, this is something you would await, as a higher amount of fine powder might result in even smaller pores in the green body. So maybe you get a lower sintering temperature or even a higher strength in the green body. But unfortunately, it's the opposite way, because yeah, you would see even a lower green body density. And the reason is that, as I showed, as I demonstrated, those fine powders will occupy the interparticle spaces between the larger particles. So, and once there is a saturation and all the interparticle spaces of the larger particles are already saturated, then an additional fine content would form layers around the larger particles. So, and this leads to an even lower green body density, and yeah, also to what does not really has an effect on the sintering temperature. And there's another disadvantage, and this is the more fine powder you add in, the higher the solid content of the fine powder, the higher would be the resulting viscosity of the slurry. And higher viscosities make it even worse with processing, or does not allow the particles to orientate and pack and arrange in a proper way during green body formation. So therefore, there's a maximum and an optimal ratio, and this is for this example with 16 percentage.
Perfect. Okay, thank you for that explanation. Another one for you. In the example shown regarding the influence of particle size on the final sintering strength, sintering conditions of 3 hours at 1600 Celsius and 1700 Celsius were selected. However, would it not be possible to achieve the same sintering strength as at 1700 Celsius for 3 hours by sintering at 1600 Celsius for 4 or 5 hours?
Yeah, so basically, this is a desire to have smaller sintering temperatures, of course. Yeah, especially since an oven with higher sintering temperature is more expensive. And of course, also energy consumption would be higher. However, the longer sintering is, the sintering temperature when it comes to long sintering processes has a disadvantage. As you need to know that during the sintering process, it forms some crystallites or grains in the dense body. So does not really refer to the particle size of the starting material, but during the sintering, you might get different orientated crystallites in the sinter body. And the longer you sinter, the more will these grains will grow, and you get a grow of the grains there, and you get less interfaces, less boundaries between those. And this effect will give a less sinter body density. Yeah, so therefore, long sintering time is not preferred. You might get as short as possible with as low as temperature as possible. Therefore, it was the fine powder, and I will need to be honest with you, it was not all the details, so it could be even better when you exchange a bit. Do not only use zirconia fine powder, but add a bit of alumina fine powder. Then you can even achieve lower temperatures and a lower sintering time. So yeah, it's really a complex thing. So, yeah.
Gotcha. Perfect. Okay, thank you for that. Wenjian, we have a few questions over here for you now. You ready for us?
Yes, I'm ready.
All right. You mentioned in your slide that up to 10 B-scan labs can be linked to the same computer. Do they run independently without interfering with each other?
Yeah, thanks for asking. That is a good question. Yes, each BitScan lab works independently without affecting each other. And each BitScan lab can perform stability analysis according to its own SOP. And even the measurement temperature and the types of the sample cell are totally different. We can use one software to control up to 10 instruments. And this increases measurement flexibility. That means we can measure different numbers of samples according to our needs. For example, if we want to measure two samples simultaneously, we can just link two B-scan labs to one computer, and we can start one stability analysis under high temperature. And at the same time, we can also perform a stability analysis for a highly viscous sample using a coring cell. And we can also start or stop each measurement individually.
Okay, perfect. Thank you. Another one. What gas is used most often for the gas pygnometer? And will using different gases have a significant impact on the results?
Okay, helium is commonly used as displacement gas in a gas picrometer for determining the true volume of the ceramic materials. One of the main reasons is that the helium is chemically inert, meaning it does not react with most types of ceramic or other solid samples. In addition, helium has an extremely small atomic size, which enables it to permeate into very fine pores and voids that may be inaccessible to large gas molecules. This ability allows helium to provide a more accurate estimation of true volume, especially for porous or finely structured ceramic. For application requiring high precision results, helium is generally considered the best choice due to its combination of low reactivity and superior penetration capability. However, for regular lab measurements, nitrogen is also a cost effective and a chemically stable options. For non-porous samples or regular ceramic powders, the difference in measured results when using different carrier gas, for example, helium, nitrogen, or carbon dioxide, are almost the same. We need to choose appropriate gas according to our demands.
Okay, perfect. Thank you for that explanation. So helium it is. All right, Freddie, back to you. We have an attendee who says if true or real density is related to mass/volume, I do not see the relation with microstructure except if you are measuring samples with open porosity. Could you explain how that works for us?
Yeah, it is explained already with the question, I think. That's right. Density is a ratio with mass and volume. But as I tried to visualize on my slide a bit, is that with different crystal structures, you might get different packing. So therefore, in the tetragonal phase, the particles are packed in a different way than in monoclinic phase. They are more packed. So therefore, not particles, sorry, atoms in the end are packed. So therefore, the crystal structure with different types of packing will have an effect on the volume and therefore on the density, of course. There's a difference in the density between monoclinic and tetragonal structure of zirconia.
Our next question for you. 3YSZ should have a value of true density. Why the range 6.03 to 6.08? Is this related to the error associated to the true density measurement?
Oh no, so therefore, if a pygnometer would have this error, then it would not be a good pygnometer. So this has nothing to do with the measurement. Then also the better pig can measure that precise and do not get this range. No, it is since 6.03, 6.08 for 3 mole percentage of yttrium oxide in zirconia. The point is that in theory, it should be 3 mole percentage. In practice, depending a bit on the manufacturing process, it is something between maybe 2.9 to 3.1. And so since yttrium oxide has a smaller density than the zirconia, this leads to this variation. And this is desirable, that the tetragonal structure or tetragonal crystal structure of zirconia is the desired one. So this comes with a density of 6.10, while the monoclinic structure has a smaller density. So therefore, if it in your starting material, it's not 100% of tetragonal crystalline, but there's a small portion of monoclinic zirconia in, then you also get a smaller density. So therefore, this range 6.03, 6.08 depend a bit on the real amount of yttrium oxide and also the purity in terms of crystal structure.
Perfect. As we want good picnometers. That's good. All right. Another one, Freddie. What was your solids loading in liquid for the zirconia size fraction study?
Oh yeah, so this was all together, it was 90 weight percentage, so a lot of zirconia in there. So this was not easy work done by a colleague of mine. So yeah, it needs a lot of optimization to get this high solid content in. And as I said before, that's why it limits. You need such high solid contents to get good green body strength or densities. So this would not be possible with only fine zirconia, that you might only get 40 to 50 weight percentage. But with the coarser ones, you can end up in total a 90 weight percentage, and then depending what was the ratio, 0, 10, or 16 weight percentage of the fine one. So 90. That's the answer.
Thank you so much. Those are very clear answers. It's very helpful. Thank you. Another one for you before we move over to Wenjian for the next few. Freddie, is it possible to measure the size of particles in a sample that is a mixture of two different materials?
Yes, we can use laser diffraction to measure the samples, including the two material. And
Freddie, anything to add there or self-explanatory?
Yeah, no, nothing really that is. Of course, this is possible if it's two different materials, but you need to know that what we get with laser diffraction is a volume-based distribution. So therefore, from pure laser diffraction, you cannot directly distinguish which type of material is what. But of course, you would see that one is smaller, one is larger. So as a result, from laser diffraction, you get the equivalent diameter. So yeah, and volume-based. So therefore, yeah, you cannot say which type of material it is, but as long as they are different in size, we will see that they are different in size, of course.
Okay. All right, Wenjian, how do you ensure sufficient dispersion of ceramic powders that are likely to agglomerate during measurements?
Okay, this is a commonly asked questions when we perform laser diffraction particle sizing. And before measurements, first we need to choose a correct dispersion module. If the sample is non-reactive in water, we prefer to perform a wet measurement rather than dry measurement, since samples can be dispersed more effectively in water. If the sample is not stable in water, we can use a dry dispersion module or we can use anti-corrosive dispersion module, and where the water is replaced by organic solvent. For wet measurement, stirring, ultrasonication, and dispersing agent are three common methods to make sure that the samples are fully dispersed. With the Bettersize 2600, circulation speed, ultrasonication power, and the feeding volume of the dispersing agents can be adjusted with the analysis software. But we need to be careful because too low circulation speed may cause sedimentation, and too high can form bubbles. Similarly, excessive ultrasonication can break up particles, and overdosing dispersing agent can lead to flocculation, for example. And for dry dispersion, the sample is carried by the venturi device, and here we can adjust the dispersion pressure, which provides shear force to break up agglomerates. And besides, there are collisions between between the particles and the inner wall of the sampling holes, which are also beneficial to dispersion. But again, caution is needed because too high pressure may damage particles. So in short, we can achieve full dispersion by carefully modify these parameters depending on the sample types.
Okay. All right, another one for you here as we get close to the end. Wenjian, do you recommend utilizing the imaging analysis with all particle size distribution measurements? How typical is it that the coarser particles, agglomerates, would be overlooked when running the laser scattering analysis alone?
Oh, that's a good question. Absolutely, you can measure with only image analysis. If you focus on a particle shape analysis, you can just use image analysis. But there is a problem, and that is we cannot use camera to capture submicron particles because the that is why we need laser diffraction, and laser diffraction applies me theory, which is designed for measuring tiny particles. So in general, we can combine these two techniques, and the laser diffraction for the small particles uh, to ensure high measurement accuracy, and the image analysis for the coarse particles to make sure that we won't overlook the coarse particles in the samples.
Got it. Thank you so much. All right, we have the last few questions here for Freddie before we wrap up. Freddie, in sanitary ware, what's the relation between particle size and drying rates and cracking? Oh, we can't hear you. Maybe make sure you unmute.
Now you can hear me, hopefully. Sorry. Yeah, okay, got it. Yeah, okay. Sanitary ware, another field where ceramics is of course used. And it's not that easy to answer. I mean, I tried it a bit to give you one example that should represent a bit or a lot of ceramics. I mean, basically, it's always a bit a mixture. How with mixed different fractions, size fractions, and to avoid cracking, as I showed you, then of course, if you have too much fine content, you might get too high viscosities, and therefore and you cannot get such high content, such high solid content. So therefore you get less screen body density, what might easily fall apart. So it's not that easy to answer just with one answer. I think that needs to have a closer look. So whoever asked this question, please do not mind to get in touch with us, and then of course we can in detail evaluate your application and discuss a bit how the instruments could help you and what might be also in terms of application be recommended. Yeah.
All right, last one for you, Freddie. What are the limits of granulometry laser?
The limits of laser diffraction in general, I think, and this is how I would interpret it, the data or the question. Yeah, I mean, I think Wenjian tried to show this also a bit. I mean, basically, in laser diffraction, we get volume-based distribution curves. I mean, what the benefits of laser diffraction is clear. It starts in the nano range, going up to the millimeter range. But especially if you have broad distributions, and especially the small particles are in terms of number always way more represented than the big ones. So maybe laser diffraction in general struggles a bit with this oversized analysis to identify the small number of large particles. It might lead you to some troubles, especially also in ceramics, but also in other fields. So therefore, there the image analysis could additionally help. And furthermore, what is a limitation in laser diffraction is that, of course, all particles are treated to be spherical, even if they're not. So if you have really shape anisotropic particles, you would not see this, basically. Here again, image analysis can help. Yeah, so, but on the other side, laser diffraction is pretty fast and it gives a wide range, so therefore it's pretty popular. But sometimes, especially for unknown samples, you might need a bit of addition in the informations, like from image analysis. So where this combination, Bettersize 2600 with PIC 1 is a good fit, especially to give you a deeper look inside.
Perfect. All right, audience, that about wraps up all the time we have for Q&A today. I'd like to thank Freddie and Wenjian for their wonderful presentations and clear answers to all of your questions today. And thank you to Bettersize as a whole for sponsoring today's webinar. In 24 hours or less, this webinar will be available on demand if you'd like to watch it again or share it with friends and colleagues. Thank you so much for attending today's webinar. We hope you have a wonderful rest of your day.
Thank you. Bye-bye.
Thank you. Bye.